Right now, as you're hearing this, something extraordinary is unfolding in our solar system. Back in July, when astronomers first detected 3 Atlas, it seemed like just another intriguing discovery. But since then, events have taken a strange and unexpected turn. This interstellar traveler, ancient and mysterious, has puzzled scientists from the very beginning. Its unusual green glow and baffling chemistry were already hard enough to explain, yet what's happening in its aftermath is even more astonishing. Our usually steady and predictable cosmic neighborhood now feels like a cosmic freeway jammed with traffic, where objects are converging in ways that look far too organized to be random. From clusters of comets showing up together, to waves of asteroids sweeping past Earth, the sky is sending signals that something is very different. And the question astronomers are now asking is simple but unsettling: what exactly is 3 Atlas doing to our solar system? Stick with me on this journey tonight, as we explore whether this is just an incredible chain of coincidences, or proof that something far more profound is unfolding above us. Take September 2025, for example. Astronomers expected a calm, uneventful month, the kind they could log into their databases and move past without much thought. Instead, what arrived was nothing less than a celestial spectacle that had researchers glued to their telescopes and everyday skywatchers stunned by what they saw. It began with the spotlight on one object. Asteroid 2025 FA22, a mountain of rock estimated between 130 and 290 meters across. On September 18th, it cruised past Earth at just over twice the distance of the Moon, about 835,000 kilometers away, distant enough to keep us out of danger, but close enough to grab attention around the globe. Yet, FA22 wasn't traveling alone. The timing hinted at something more coordinated, almost theatrical, as if the universe had planned an opening act followed by an encore. Only days earlier, on September 15th, a much smaller object, 2025 RJ2, had zipped past us at a strikingly close 0.78 lunar distances, which is around 300,000 kilometers. At that scale, cosmic terms or not, it felt almost intimate, like the universe had reached out for a handshake. And the surprises didn't stop there. That same week was crowded with additional asteroids cutting nearby paths on sublunar distances, each one tracked and catalogued by vigilant observatories across the globe. While astronomers are used to numerous small objects buzzing around us, this particular clustering didn't feel ordinary. It gave the impression of a schedule, as though these visitors had all shown up together for dramatic effect. But the cosmic cast wasn't made up of asteroids alone. Adding to the spectacle was Comet Situ 2025 R2, picked up by the Swan instrument aboard the SOHO spacecraft on September 11th. By mid-month, it was brightening enough to tease the edges of naked-eye visibility in the constellation Virgo. Its sparkling tail stretched majestically across the twilight sky, a glowing streak anyone could see if they knew where to look after sunset. Like many comets making their fiery runs near the sun, its long-term survival was uncertain. Some break apart, leaving behind nothing but shimmering debris trails marking their brief existence in our skies. Still, for the moment, it was another striking reminder that this September was unlike any other. Threaded throughout all these astronomical headlines was an infamous name: Apophis. Officially catalogued as asteroid 99942. Apophis, it once topped every planetary defense concern list. This massive space rock, approximately 400 meters across, is destined for an uncomfortably close approach to Earth on April 13th. 2029. When that day arrives, it will pass at just 32,000 kilometers, closer than the satellites that orbit our planet. Moving at a breathtaking 50,000 kilometers per hour, it will blaze across the night sky bright enough to see without a telescope. Just mentioning it is enough to stir a mix of curiosity and unease whenever new celestial events appear. Yet, even with all these dramatic visitors, none of them could overshadow what was waiting in the wings. In July, astronomers at the Atlas survey in Chile made a discovery that was immediately recognized as unusual: Dicilish 2025 N1, or as we now call it, 3 Atlas. At first glance, it looked like just another faint smudge among the stars, but as computer models refined its orbit, the extraordinary truth became undeniable. This was no ordinary comet. This was only the third known interstellar visitor ever confirmed, traveling fast enough along a hyperbolic orbit to escape our sun entirely. It didn't belong to our solar system at all. It came from somewhere else. Another star system, perhaps light years away, and after a brief encounter, it would vanish back into the endless black, never to return. What made 3 Atlas even more breathtaking was how perfectly timed its arrival seemed. Its closest point to the sun, perihelion, was set for late October 2025, not long after the September wave of asteroids had made headlines. Like a performer about to exit stage left, it would vanish into the sun's glare for several weeks. But patience would pay off, because by early December Earth's position would shift, offering us the perfect angle to see it again, as it emerged from the solar glare. That second act would give telescopes their best chance to examine an untouched fragment of material from another star system. Not only would it be incredibly close in astronomical terms, about 1.88 astronomical units, or roughly 270 million kilometers, but it would also pose no threat, cruising along at just the right distance for deep investigation. It was like the universe had hand-delivered a gift, dropping off a sample from the stars with just the right timing, the right distance, and the right conditions for us to study. For scientists eager to decode the chemistry of distant worlds, it felt too perfect to dismiss as coincidence. And yet, that perfection fueled more questions. Why here? Why now? Part of the answer lies in technology. Observatories like the Vera C. Rubin, which only began operating in June 2025, can detect thousands of new asteroids in mere hours. With sharper eyes in the sky, we're suddenly uncovering just how crowded and unpredictable our cosmic neighborhood truly is. But there's still an eerie sense that something larger is connecting all these events. The timing felt almost too perfect, too orchestrated to chalk up to simple coincidence. Was something unique happening in September 2025? Could a subtle interplay of gravity, or perhaps a seasonal alignment, have drawn these visitors together? Or were we glimpsing the opening scene of a much bigger cosmic story, one that stretches out on timescales far beyond human imagination? Astronomers weren't panicked, but the mood was charged with curiosity and urgency. This wasn't a world where asteroid impacts belonged strictly to disaster movies anymore. Humanity had come a long way. Planetary defense had advanced to the point where we could detect, study, and even alter the course of incoming objects. NASA's DART mission had already proved an impactor could nudge an asteroid off its trajectory, while Europe's Hera spacecraft was headed out to dissect the aftermath in detail. But even with such tools at hand, one uncomfortable truth lingered: all those preparations meant little without time. What about the ones we couldn't see yet, shielded by the sun's glare until their approach was fatally imminent? It was a sobering thought. Had 2025 FA-22 been on a direct collision course rather than sailing by at a safe distance, would we honestly have had enough warning to react? And then there was the deeper riddle posed by 3 Atlas itself. With alien chemistry and an interstellar origin, it hinted that the galaxy might be filled with countless unseen wanderers drifting between star systems. The sudden surge that September didn't trigger paranoia, it sparked recognition. A collective awareness settled in. We were no longer looking at a small, stable backyard. The solar system appeared far more dynamic, far more tangled into the larger galaxy than we'd allowed ourselves to believe. For humanity, it felt less the end of a chapter, and more the beginning of a new one. The moment we realized that being a planetary species wasn't enough. If we were to endure, we had to see ourselves as participants in galactic-scale events. But all of that big-picture thinking still hinged on one immediate question: what would have happened if FA-22 hadn't passed harmlessly by? Asteroids don't play fair when they collide with planets. The physics is straightforward and merciless. On September 18th, as FA-22 skimmed past Earth at 835,000 kilometers, it carried with it an astonishing amount of energy, comparable to about 100 megatons of TNT. Put another way, that's 2,000 times more powerful than the atomic blast that leveled Hiroshima, compressed into a rock only a couple hundred meters across. But in impact scenarios, energy alone doesn't tell the whole story. The real devastation depends on how it's delivered, what the object is made of, at what angle it enters the atmosphere, and the sheer luck of where it comes down. Sometimes the difference between widespread devastation and planetary survival is as simple as whether the rock is solid iron or loosely packed rubble. FA-22 was moving at about 10.8 kilometers per second, a typical speed for near-Earth objects. At that velocity, entry through our atmosphere would have been nothing short of catastrophic. As it plowed downward, walls of air would compress until they formed a plasma sheath, heating the asteroid's surface to temperatures of several thousand degrees, all while it was still high above the ground. To the naked eye, it would appear as a second sun blazing across the sky, visible from hundreds of kilometers away. In reality, though, the most probable outcome for an object of its size and composition would be an airburst, an atmospheric detonation occurring somewhere between 5 and 15 kilometers above the surface. History offers a chilling parallel. In 1908, A smaller asteroid exploded in the skies over Tunguska, Siberia, flattening over 2,000 square kilometers of forest, with a blast equivalent to 3 to 15 megatons of TNT. No crater, just devastation, etched into the landscape. Now imagine scaling that up many times over. A 100 megaton blast in the skies would paint a horrifying picture. Standing 200 kilometers from the impact zone, you'd first see a flash more brilliant than daylight itself, intense enough to blind eyes and ignite dry vegetation instantly. The heat pulse would last long enough to burn unprotected skin, as far as 100 kilometers away. Moments later, the shockwave would arrive with a force few buildings could withstand. Windows would shatter across areas larger than small nations. Homes would splinter in regions stretching tens of kilometers from ground zero. Even reinforced concrete would falter under the crushing overpressure within the inner blast radius. And that's only one of the possibilities. Had FA-22 been denser, say a metallic asteroid, and managed to push deeper into the atmosphere before breaking apart, it might not have disintegrated in mid-air. Instead, it could have slammed into the ground with unimaginable force, carving a crater 3 kilometers wide and half a kilometer deep. The explosion would vaporize both the asteroid and a massive volume of Earth itself, throwing molten rock skyward. Ton after ton of debris would rain back down, starting wildfires, collapsing infrastructure, and shaking the Earth with the fury of a magnitude 6.5 earthquake. But perhaps the most terrifying scenario would not take place on land at all, but at sea, with over 70% of Earth covered by water. Statistically, that's the most probable target for a rogue asteroid. And when rocks of this size hit oceans, they generate monsters, tsunamis. Early modeling suggests a 200-250 meter asteroid colliding with deep water could throw up a wave over 100 meters tall at the point of impact. These walls of water don't fade quickly. They travel across entire ocean basins at speeds rivaling a jet plane. A mid-Atlantic hit, for instance, could mean 10-meter waves hammering both American and European coastlines within hours. Cities from Boston to Barcelona could be inundated. Still, the reality of waves is nuanced. As they travel, their heights drop with distance, stretching out and diminishing due to the effects of geography and ocean depth. A 100-meter behemoth at the site of impact might fall to 10 meters by the time it strikes land 60 kilometers away. That variance is why details like coastal shape and seafloor depth become life or death factors when predicting tsunami risk. The crucial point is that FA-22, as destructive as it might have been, wouldn't have been a civilization-ending asteroid. It could destroy a region, kill millions, and leave scars on both human history and the planet itself. But global climate effects, mass extinctions, or the collapse of humanity, that level of catastrophe requires kilometer-sized behemoths, the kind that strike every few 100,000 years. FA-22 wasn't one of those, yet it was still dangerous enough to be a wake-up call. For perspective, think back to February 2013 and the Chelyabinsk event in Russia. That rock was only about 20 meters across, barely a fraction of FA-22's size. Yet when it exploded over the city, it still generated a blast equal to 500 kilotons of TNT. Over 1,500 people were injured, mostly from flying glass shattered by the shockwave. The dashcam footage of that fireball reminded the world that space doesn't need to send mountains to devastate us. Even modest rocks can change everything in a matter of seconds. But the most haunting lesson of Chelyabinsk wasn't the damage. It was the blindness. That asteroid came from the direction of the sun, completely invisible to Earth's detection systems until the moment it entered our skies. No telescope saw it coming, no warning was ever issued. This is the unguarded corridor in our planetary defense. Objects approaching from the sun's glare can slip through undetected until it's too late. FA-22's flyby, though harmless in itself, offered the world something priceless. A test run. It gave planetary defense teams a real scenario to rally around, refine tracking systems and rehearse responses. For a brief moment, FA-22 even appeared on the European Space Agency's risk lists before it was quickly downgraded once improved orbital data came in. That false alarm turned out to be a live test in one of the most difficult challenges modern science faces. How do you tell the world about a possible threat without creating unnecessary panic? And if such a threat really existed, how do you coordinate a global response for something that could affect multiple nations at once? In this case, the International Asteroid Warning Network treated FA-22's approach like a drill under real-world conditions, running through communication systems, coordination methods, and observational checks. Even though the danger passed without incident, the exercise itself was invaluable. It proved the framework could function under stress. But at the same time, the encounter exposed how fragile our defenses still are. In planetary protection, time is everything. The earlier we detect a dangerous object, the gentler the intervention required. A tiny nudge applied years in advance can make all the difference compared to desperate, last-minute interventions. Right now, kinetic impact, the strategy NASA demonstrated with the successful DART mission, is our key defense, essentially slamming a spacecraft into an asteroid at high speed to knock it slightly off course. The method works, but it demands precise knowledge of the target. A loose rubble pile responds very differently than a dense slab of iron. Miscalculate, and instead of deflecting a threat, we might split it into multiple, equally dangerous fragments. FA-22 acted as a sharp reminder that Earth sits in the middle of a cosmic firing range. Most of the incoming projectiles are just dust and sand-sized particles that harmlessly vaporize as meteor showers, giving us nothing more than dazzling night sky displays. But every so often, a larger body sneaks through, and when it does, the consequences scale dramatically, from local destruction to global catastrophes, depending on size and luck. Fortunately, progress is accelerating. State-of-the-art survey telescopes, now coming online, are able to detect faint objects with far greater accuracy, and soon, space-based infrared observatories will fill in the dangerous blind spot, those objects approaching from the sun's direction that our ground-based telescopes simply can't see. The Chelyabinsk impactor, back in 2013, arrived from that very corridor, completely undetected, until it lit up the Russian sky. With upcoming missions, the hope is to close that vulnerability once and for all. And yet, just as our net grows stronger, discoveries like 3 Atlas remind us how big and unpredictable the universe really is. Our solar system isn't a closed bubble. It's more like a stopover on a galactic highway, constantly visited by travelers from far beyond. That interstellar visitor forced astronomers to step back and wonder if the September surge was just chance, or if there's an unseen connection between FA-22, the other near-Earth asteroids that month, and the mysterious green glowing outsider streaking in from another star system. While scientists wrestled with that puzzle, another player was quietly stepping into the spotlight. As FA-22 made headlines for its close shave with Earth, a comet, designated CES 2025 R2, was rapidly preparing for its debut in the autumn skies. Picked up on September 11th by the Swan instrument aboard the Soho spacecraft, it quickly became one of the hidden highlights of the season. What made the discovery remarkable was that Swan wasn't even designed to search for comets. Its true mission is to track hydrogen emissions from solar-wind interactions. But when an icy body begins its dive toward the sun, it releases enormous amounts of water vapor, and that vapor glows in Swan's detectors like a cosmic beacon. In other words, the comet revealed itself by screaming out its hydrogen signature across millions of kilometers of space. By mid-September, R2 had brightened enough to reach 6th magnitude, hovering right at the edge of naked-eye visibility under dark rural skies. Amateur astronomers soon began spotting it near Virgo at sunset, close to the brilliant star Spica and the red tint of Mars, just above the western horizon. A glowing tail began to unfurl from its side, stretching out like a brushstroke across the fading twilight, the kind of sight that has fired human imagination for thousands of years. But comets are fragile, temperamental bodies, very different from asteroids, which are often slabs of rock or metal. Think of them as dirty snowballs, mixtures of ice, dust, and complex organics loosely glued together by weak gravity and frozen chemistry. When the sun's heat reaches them, the same forces that create their spectacular tails can also rip them apart. Many comets discovered by Swan never survive their fiery passage, crumbling into debris showers that briefly light the skies before vanishing completely. The way this happens comes down to delicate physics. Water ice begins transforming directly into vapor around 200 Kelvin. More volatile materials like carbon dioxide or methane start out gassing even earlier, far from the sun. This pressure builds jets that go shooting into space, sometimes strong enough to push the comet off its mapped path. That makes the orbits of new or long-lost comets notoriously hard to predict. Fresh comets from the far reaches of the Oort cloud are especially vulnerable. Their pristine ices, untouched for billions of years, explode into vapor the moment sunlight warms them. The stresses inside can tear the nucleus apart into multiple pieces, each sprouting its own faint tail, or it can disintegrate into nothing more than a fading, glowing cloud of cosmic dust. Even as Comet Oort 2 was dazzling backyard stargazers, another cosmic heavyweight was preparing to dominate headlines. Asteroid 99942 Apophis, a massive rock nearly 400 meters wide, remained on its slow, inevitable course toward what will be the closest flyby of a large asteroid in human history. On April 13, 2029, Apophis will sweep past Earth at just 32,000 kilometers, sliding in closer than many of our communication satellites. That night, anyone on the planet will be able to step outside and see it with the naked eye. It won't be a faint smudge or a distant light point you need a telescope for, but a star-like object racing across the night sky so quickly you'll actually be able to watch it move in real time, and it will be screaming past at an incredible 50,000 kilometers per hour. What makes Apophis so compelling is not only its closeness, but the certainty. Scientists know, with absolute precision, that it will not strike Earth, not in 2029, nor in the decades that follow. Radar scans and years of optical tracking have pinned down its path with extraordinary accuracy. That knowledge gives astronomers something rare, the chance to study a large asteroid during an extreme close approach without the specter of fear. Earth's pull, however, won't leave Apophis unchanged. As it sweeps past, our planet's gravity will stretch and tug at it like a sculptor's hand, slowing its spin, shaking loose its surface rubble, and possibly triggering landslides or shifts across its regolith. When Apophis departs, it will not be the same asteroid it was before. To capture this unique transformation, NASA has repurposed its successful OSIRIS-REx spacecraft into OSIRIS-APEX, tasked with rendezvousing with Apophis soon after the flyby. It will map the aftermath in exquisite detail, measuring exactly how Earth's tidal forces reshaped its structure and surface. That information is priceless for the future of planetary defense. If humanity ever needs to deflect a world-ending rock, understanding how asteroids respond to sudden gravitational and mechanical stresses will be critical. The timing of Apophis's historic rendezvous with Earth, arriving only 3.5 years after the chaotic September 2025 surge, can't help but raise questions. Are we witnessing a temporary string of coincidences, or has something about the solar system's orchestration shifted? Statistically, asteroid flybys don't follow human patterns. They're governed by the complex gravitational dance of planets and smaller bodies, spanning billions of years. Yet the clustering of high-profile encounters into such a narrow window seems to resist simple explanations of randomness. Part of the story lies in how much better we've become at watching the skies. Over the past 2 decades, sweeping projects like Linear, NEAT, and Spacewatch revolutionized the cataloging of near-Earth objects. And in June 2025, the Vera C. Rubin Observatory switched on, marking another leap. With its enormous field of view and hypersensitive detectors, it can now scan the entire visible sky every few nights, dramatically boosting our ability to spot faint newcomers and track objects we thought we already understood. The result, we see more and faster than ever before. But while better detection explains part of the surge, it doesn't answer the full mystery. September 2025 wasn't just about FA22 or Comet R2. That month, the skies were crisscrossed with dozens of smaller near-Earth asteroids, weaving through our local neighborhood in unusually tight clusters. One of them, 2025 RJ2, passed within just 0.78 lunar distances on September 15, practically brushing our cosmic doorstep. Multiple sublunar encounters followed, each carefully logged by the Global Space Surveillance Network. Why so many, and why then? One possibility is that Earth's position in its orbit carried us through a denser patch of debris, a swarm resulting from past collisions in the asteroid belt. Another theory suggests deeper resonances at play, complex gravitational rhythms that can synchronize or cluster the orbits of many bodies over immense timescales. And then there are the comets. Unlike their steadier asteroid cousins, comets are unpredictable. Outgassing jets can kick them off course without warning, while the giant planets constantly tug and redirect their paths. Long-period comets that come screaming in from the Oort cloud often arrive on their first visit in millions of years, completely unannounced. They serve as wildcards in the solar system's deck, reminding us that even the best predictions can be upended by a puff of gas on an icy surface. For the public, terms like asteroid, comet, and meteor often blur together, but each holds a distinct role in this celestial theater. Asteroids are rocks and metals left over from planet formation, predictable to a degree, though dangerous when they stray close. Comets are dirty icebergs, fragile and volatile, prone to fragmenting into spectacular, and sometimes hazardous, displays. Meteors are nothing more than the final shimmer of debris burning in our sky, remnants, whether from an asteroid or comet, that usually fall harmlessly, but occasionally leave behind chilling scars. Together they're fragments of the solar system's story, relics of how planets formed and worlds began. September 2025 showed us all three, in dazzling variety, pieces of the asteroid belt, messengers from the frozen edges of our system, and hints of chaotic motion playing out all around us. But the greatest surprise was still to come, one that would steal the stage from everything else. The comets and asteroids of autumn were all local visitors, tied to our sun. The next arrival was something entirely different, a traveler not born of our solar system at all. On July 1st, 2025, a faint dot of light flickered into existence on images captured by the Atlas survey in Rio Hurtado, Chile. At first, it was nothing remarkable, just another candidate among thousands. But as its orbit was pinned down, the truth became unavoidable. This object was not bound to our sun. It was racing through space on a hyperbolic path, a genuine visitor from beyond, carrying with it the secrets and chemistry of another star system. It would soon be known as 3 Atlas, and it was about to challenge everything astronomers thought they knew about the universe. The math left little room for doubt. As additional data refined its orbit, one value stood out with stunning clarity: its eccentricity was greater than 1. In orbital mechanics, that's the unmistakable signature of a hyperbolic path, a trajectory carrying enough speed to break free from the sun's grip altogether. This object wasn't part of our solar system. It was a visitor, just passing through. Astronomers named it 3 Atlas, only the third confirmed interstellar object ever discovered, following the enigmatic cigar-shaped Oumuamua in 2017 and Comet 2I/Borisov in 2019. But unlike those fleeting guests, Atlas arrived under conditions that gave us time to track it, study it, and uncover its secrets. Its orbit lined up beautifully for science. Closest approach to the Sun, its perihelion, was calculated for October 30th, 2025. Then, just weeks later, in December, it would skim by Earth's vicinity at about 1.8 astronomical units, or roughly 270 million kilometers. That's too far to pose any danger, but close enough for our most powerful telescopes to gather remarkably detailed data. It felt less like chance, and more like a cosmic delivery, a pristine package from another star system arriving at exactly the right angle and the perfect time. But its path was only the beginning of the mystery. As observations rolled in through summer and autumn, Atlas began to behave not just oddly, but astonishingly. Hubble data suggested its nucleus was likely no larger than a few kilometers across, modest in size compared to many comets. Yet as it approached the Sun, it developed the unmistakable features of a classic comet, something Oumuamua never displayed. By September 2025, telescopes were already resolving a glowing coma, with a tail beginning to stretch out behind it. For the first time, we were watching an interstellar intruder reveal its chemistry in the same language as our local comets. The James Webb Space Telescope soon locked its gaze on Atlas, and what it found shocked astronomers. The gas cloud surrounding the nucleus contained an unusually high concentration of carbon dioxide compared to water vapor, among the highest ever recorded. Normally, in planetary systems like our own, water ice condenses in the middle regions of the system, while carbon dioxide forms much farther away, beyond the snow line in the deep freeze. The dominance of CO2 in Atlas implied something extraordinary. Either it formed in the frigid outskirts of its parent system, allowing little water ice to accumulate, or it condensed from material unusually rich in carbon dioxide. But the chemical surprises didn't stop there. Observations from the Very Large Telescope in Chile revealed bright nickel emission lines with strangely faint iron signatures. In our solar system, iron and nickel show up in similar quantities, remnants of the star-forming cloud that birthed us. Atlas somehow was different. The ratio suggested a chemical fingerprint unlike anything we've encountered nearby, clues pointing to environments and processes foreign to our corner of the galaxy. As autumn wore on, and the comet drew closer to perihelion, its visual display grew dramatic. Gemini Observatory, and other powerful eyes on the sky, began documenting multiple distinct tails, each flowing in slightly different directions. These variations meant that sections of the comet's surface were activating at different times, releasing different substances under solar heating. After billions of years adrift in frozen interstellar night, Atlas was waking up under the sun's fire, roaring to life in spectacle. Yet, even as it grew brighter, a frustrating barrier rose. By late October, the comet's position brought it dangerously close to the sun in our sky. The glare made direct observation nearly impossible, hiding Atlas from many instruments at precisely the phase when it might reveal the most. Astronomers could only wait and trust that November's orbital geometry would slowly swing it into a better vantage point. Patience was rewarded by early December. Atlas would re-emerge in a prime viewing position, once again visible for extended observation. At closest approach, while still nearly 200 times farther than the Moon, the comet would remain an ideal target for long-duration spectroscopic campaigns. The scientific community buzzed with anticipation. Would its unique chemical profile hold steady, or would higher solar heating peel back its crust to expose new, hidden layers? More importantly, would Atlas survive perihelion at all, or would it splinter apart like so many fragile comets before it? Some of the earliest orbital studies suggested Atlas wasn't just another interstellar rock. It might be ancient on a scale almost beyond comprehension. If its velocity lined up with the population of stars in the galaxy's thick disk, it could be older than our Sun itself. That would make Atlas a messenger from an era before Earth even existed, holding within its icy body the frozen chemistry of a very different galaxy, billions of years in the past. This alone set it apart from Oumuam's puzzling departure, and Borisov's brief flyby. Atlas's path and moderate velocity bought us time to study, time to measure, time to dig deep into its alien structure. Astronomers estimated the object would remain observable well into 2026, giving humanity an unparalleled chance to study a piece of another star system in long, sustained detail. And yet, the bigger mystery lurked behind the numbers. Where had it come from? How long had it wandered alone between the stars? What event, perhaps a violent planetary collision, or the early instability of a star system, had ejected it into eternal exile? Stranger still was the eerie timing. Atlas made its entrance directly following a month filled with extraordinary asteroid and comet activity in our own neighborhood. Was this chain of events just chance stacked upon chance, or did the synchronization point to something deeper, some larger dynamic shaping the stage? One after another, the cosmic surprises had unfolded. The September parade of asteroids, the glowing rise of a new comet, and now this interstellar emissary blazing with alien chemistry. The possibility that they were all unrelated coincidences strained belief. It began to feel as though the universe was revealing a pattern, one we only dimly understood. As Atlas slipped behind the blinding radiance of the sun, and astronomers waited for its return in December skies, one truth was undeniable. This object was already reshaping our understanding of planetary formation, cosmic chemistry, and humanity's connection to the wider galaxy. The question was no longer whether Atlas would give us answers. It was whether we were fully prepared to face what those answers might reveal. The true mystery was only beginning to take shape. While 3R Atlas captured the spotlight with its alien chemistry and ancient pedigree, an increasing number of astronomers began noticing something unsettling in the background. September's cascade of activity didn't look random. There were patterns too suggestive, too timed, to dismiss as simple coincidence. And that realization triggered a broader question about planetary defense. Just how ready are we really when the cosmos decides to test us? What September 2025 delivered was less a spectacle and more a warning, a sharp reminder of how fragile Earth's defensive posture remains, even after decades of innovation and global cooperation. Yes, we managed to track every notable rock that came near us during that chaotic month. But the clustering of those encounters exposed cracks in the system, gaps that under different circumstances might have spelled disaster. At the heart of the problem lies the geometry of detection. Almost every asteroid hunting telescope we have sits on Earth's surface, scanning the skies at night. The limitation is obvious. Nothing can be seen in the direction of the sun. That blind spot is enormous. And ironically, it's the exact corridor that delivered the Chelyabinsk impactor back in 2013. That fireball came from the daytime sky, its blinding approach hidden by the sun until the very moment it struck. A larger object sneaking in through that same approach path would feel, to us, like a punch out of nowhere, hours of warning at best. Asteroid FA22 happened to come from a friendly angle, giving us weeks of advanced tracking. But if its orbit had tilted slightly differently, placing it on a sunward trajectory, we might have had nothing more than a frantic scramble with hours to act. This single blind spot represents perhaps the most dangerous vulnerability in humanity's planetary defense network. Ground-based telescopes have made leaps forward, yet they are shackled by the most unavoidable rule of optics. You can't see past the brightest object in the sky. The solution lies beyond Earth. For years, scientists have called for space-based surveys, and finally, some are in the works. NASA's Near-Earth Object Surveyor, a dedicated infrared space telescope, is scheduled to launch in 2027, trailing Earth's orbit. From that vantage point, it will peer into the very corridor that blinds us from the ground, detecting asteroids that would otherwise remain invisible until it's too late. It will be our first true set of eyes where we need them most. But spotting a threat is only step one. Once an object is located, we need to determine, is it dangerous? That requires precise orbit calculations, fast follow-up from multiple observatories, and measurements of the object's composition and structure. That's where instruments like the Vera C. Rubin Observatory come in. Switched on in June 2025, Rubin already proved its worth within hours, detecting thousands of new asteroids in a single night. With its sweeping field of view, it will rescan the entire sky every few nights, essentially giving humanity a rolling update of everything that moves against the stars. That, however, only covers awareness. Awareness means nothing if we can't act. This is where defense shifts from watching to doing. NASA's 2022 DART mission demonstrated for the first time in history that an asteroid's orbit could be deliberately changed. A spacecraft slammed into a moonlet named Dimorphos, reducing its orbital period by 32 minutes, far beyond mission requirements. The deeper lesson came in the details. The deflection was multiplied by the debris blast the impact unleashed. That rubble acted like rocket exhaust, amplifying the push nearly fourfold. Understanding this amplification effect is now critical for designing any future deflection mission. Europe's follow-up mission, Hera, en route to Dimorphos's parent system, will arrive in 2026. It will map the crater, measure the ejected material, and give scientists the ground truth data that models desperately need. Together, DART and Hera mark the first time humanity has rehearsed shifting the path of a celestial body, our first real move against the firing squad of space. Still, kinetic impactors are only one option in a larger arsenal. For threats that are too big or too complex, scientists have imagined other tools, gravity tractors, spacecraft relying on nothing but their own tiny pull to gradually tug an asteroid off course. Nuclear standoff blasts to vaporize surface material, creating thrust powerful enough to steer giants. Even futuristic ion beam shepherds, firing particle streams to nudge rocks away with a whisper of continuous thrust. They all share one common requirement: time. If you have years, even decades, these subtle pushes can save the planet. But if weeks are all you're given, all the theory in the world won't matter. That's why early detection doesn't just mean preparation for disaster. It defines whether the disaster can be prevented at all. The difference between a gentle nudge and an impossible emergency comes down to whether we spot the rock while it's still far away, invisible to all but our most advanced instruments. FA-22's temporary listing on risk charts gave international agencies something rare: a chance to practice under pressure. It forced the European Space Agency, NASA, and their partners to wrestle with one of the hardest dilemmas. When do you raise the alarm? How do you strike the balance, inform the public without igniting panic? How do you coordinate between nations when the threat doesn't belong to one sky, but to all? The International Asteroid Warning Network treated it like a live drill. The risk was ruled out fast, but the process gave everyone data far more valuable than a press release. It proved the system could hold under stress, yet it also showed the cracks that still need filling before the next, less forgiving test arrives. The lessons from FA-22's close pass revealed a mix of confidence and vulnerability. On the positive side, the quick global sharing of telescope data worked exactly as intended. Within days, scientists narrowed the asteroid's orbit, ruled out impact, and safely removed it from international risk lists. But the way the story reached the public was less reassuring. Some news outlets sensationalized the initial risk, while others ignored it completely until the all-clear had already been announced. This inconsistency speaks to one of the hardest challenges in planetary defense communication. When an asteroid is first discovered, astronomers have only fragments of data. Early orbital solutions are hazy, creating broad uncertainty zones. That uncertainty often includes both harmless and potentially catastrophic possibilities. With time and follow-up observations, the uncertainty shrinks and the orbit becomes clear. But in the early stages, the tension is sharp. Do we wait for certainty and risk losing precious time if the object is inbound? Or do we sound the alarm early and risk needless panic? Or worse, public mistrust if the warning is later retracted? September 2025 was a reminder that communication, as much as technology, defines the success of planetary defense. And the surge raised other uncomfortable truths. Long-period comets, for example, remain a lurking wildcard. They spend most of their time at the icy edges of the solar system, invisible to our telescopes, until they make a sudden dive inward. By the time one appears, the warning time can be dangerously short. Comet Swift-Tuttle, for instance, will return in 2026. Its nucleus is massive, about 26 kilometers across, large enough to cause global devastation in a direct hit. We know its orbit is safe for now, but comets like it remind us of the kind of power locked away in those outer reaches. The objects that most trouble planetary defense experts today, however, are not giants like Swift-Tuttle, but the so-called city killers, rocks between 100 and 300 meters wide. They're not large enough to bring about mass extinction, but they are more than capable of leveling entire regions and killing millions. The tragic irony is that these medium-sized bodies are also the hardest to spot. Thousands of them are still uncharted. September's parade underscored this vividly. While FA-22 made headlines, dozens of smaller objects were also buzzing past during the very same week. Imagine if more than one had come simultaneously from different directions. Could our current systems track them all with the detail required? And if more than one had been a threat, would we have the capability to launch multiple deflection missions at the same time? The honest answer is not yet. This is why investment in the next generation of defenses is critical. Instruments like the Vera Rubin Observatory are transforming sky surveys, rapidly expanding our map of near-Earth asteroids. NASA's NEO Surveyor, launching in 2027, will scout in infrared from space, closing the deadly blind spot near the Sun. And kinetic impact missions like DART, reinforced by the European Hera probe's upcoming analysis, are giving us our first real-world proof that asteroids can be nudged safely off course. But these remain the opening steps in what must be a long, sustained effort, an intergenerational commitment to cosmic safety. Unlike other natural disasters, earthquakes, volcanoes, tsunamis, asteroid impacts are fully preventable. The science is sound, the physics of deflection are straightforward, and the technology already exists. What's needed now is willpower, steady funding, steady planning, even during the quiet years when impacts feel like distant science fiction. Planetary defense is like fire insurance. You hope you never use it, but when the day comes, it might be the difference between survival and catastrophe. The September surge screamed this lesson into focus. We live in an impact zone. The Earth is not separate from the vast shooting gallery of space. It's only a question of when the next strike will happen. Yet while astronomers catalogued one asteroid after another, and as 3I Atlas drifted closer with its alien chemistry, a new tension began to take hold. The timing bothered people. The clustering of trajectories, the strange choreography of so many events in such a short span, and the eerie coincidence of an interstellar wanderer arriving at the same moment, these patterns were starting to push statistical plausibility. Our minds are naturally wired to see patterns. It's survival instinct, sharpened on savannas where spotting danger in shapes and shadows could mean life or death. That instinct can betray us when applied to the noise of the cosmos, encouraging us to weave narratives of control and conspiracy into what might simply be randomness. But sometimes, the patterns are real. Look at the sequence. On September 15th, asteroid RJ2 swept just 0.78 lunar distances from Earth. 3 days later, FA-22 passed within twice the distance of the Moon. In the same week, multiple other near-Earth asteroids crossed close by. At the same time, Comet SILS 2025 R2 flared in Virgo, inching toward naked-eye visibility, and looming quietly in the background. 3I Atlas, a traveler from another star, perhaps older than Earth itself, moved steadily toward perihelion. Individually, none of these events were shocking. Dozens of asteroids pass Earth each month. Comets brighten and fade with seasonal regularity, and every so often, by pure chance, an interstellar fragment drifts through our solar system. But packed tightly into a single frame of weeks, the events began to strain explanation. What were the odds that a comet would reach visibility in the very same stretch when so many asteroids arrived together, that an interstellar object would show up against the backdrop of it all? Some scientists tested more speculative ideas. Could Atlas itself have been responsible? Could its passage through the solar system have subtly influenced smaller bodies, shepherding them inward in a kind of gravitational entourage? But the math quickly crushed this theory. Even at its maximum estimated diameter of about 6 kilometers, Atlas carried far too little mass to tip the orbits of objects millions of kilometers away. Newton's law of gravitation is unforgiving. The force weakens rapidly with distance, vanishing into irrelevance at these scales. And orbital data didn't support it either. None of the asteroids detected that September bore signs of a common history or shared disturbance. Their trajectories were all independent, shaped by their own long dynamical evolutions. In short, the physics denied a direct causal link, but the unease remained, because if we were not looking at a literal gravitational connection, then we were forced back to two uneasy choices: an extraordinary coincidence, or some hidden mechanism we had yet to uncover. FA-22's orbit was nothing unusual. It followed the kind of path common to near-Earth objects, slightly elliptical, slightly tilted, that matched expectations perfectly. The smaller asteroids discovered throughout September also looked normal, each displaying the variety of orbital elements we routinely see. None bore the telltale signature of a hyperbolic path that would betray an interstellar origin. In other words, the spikes of activity weren't caused by 3I Atlas gravitationally stirring things up. A simpler explanation made more sense: better detection. With the Vera C. Rubin Observatory powering up in June 2025, our view of the skies changed overnight. Suddenly we weren't missing what was happening, we were catching nearly everything. Think of it like installing high-definition security cameras in a place you once barely monitored. The number of people walking through hasn't changed. They were always there. But once you start watching with sharper eyes, you notice them all. That's what Rubin did to the asteroid population. The density of space rocks hasn't suddenly increased. Our awareness of them has. Then comes the human factor. Psychologists call it apophenia, the tendency to see patterns in random noise. It's the same instinct that lets us spot faces in clouds, or hear ghostly whispers in static. Once FA-22 and others made headlines, the public and even the scientific community became hyper-alert. Every subsequent asteroid, even those that might have gone unnoticed in a duller month, felt like evidence of a bigger story. This created a feedback loop. Attention drove coverage, coverage drove perception, and soon the clustering of events seemed uncanny, when the reality may have been less dramatic. Still, some details nagged even the most sober-minded experts. The fact that 3I Atlas just happened to rise into prominence at precisely the time near-Earth objects appeared in rapid succession stretched coincidence to its edge. Statistically, it looked unlikely, a perfectly timed interstellar arrival exactly as our defenses were stress-tested by a rush of asteroids and a brightening comet. That encouraged more speculative thoughts. What if Atlas wasn't truly alone? Suppose it was a survivor of a much larger parent body that fragmented over eons as it wandered between stars. Interstellar dust impacts, internal stresses, or ancient collisions could have splintered the original mass. In that case, Atlas might be the largest surviving shard of a whole swarm. Could some of the September asteroids have been its kin? Smaller fragments captured in solar orbits during earlier passages. Perhaps they were arriving like stragglers behind a comet's lead horse. On the surface, this story was enticing. But reality intruded. Spectroscopic studies of the September asteroids showed plain, familiar chemistries, carbonaceous and silicate-rich types identical to native solar system bodies. Their reflective features matched known asteroid categories, with no hint of Atlas's bizarre chemistry. If they had shared an interstellar pedigree, their chemical fingerprints would stand out in unison. They didn't. Orbital dynamics only sealed the case further. None of the September visitors were on hyperbolic escape paths. They were bound to our Sun, tracing orbits established long ago, utterly unlike Atlas's runaway interstellar trajectory. The energy required to capture genuine interstellar debris into stable near-Earth orbits is practically impossible through natural gravitational interactions. Which leaves us, frustratingly, with the most mundane explanation. Chance, multiple lightning strikes across the sky, rare but not impossible, clumping together to create the illusion of pattern. The cosmos doesn't owe humankind an even distribution of events on convenient timescales. Pure randomness can cluster, and when it does, it often feels uncanny to creatures wired to find meaning in noise. The truth may be that September 2025 wasn't special in the universe's eyes. It was special only in ours because we watched with better instruments and relentless attention. And yet, even as dispassionate logic points toward coincidence, the nagging impression of timing refuses to fully fade. Atlas chose its moment well, arriving with its alien chemistry, its peculiar features, and its ancient, possibly pre-solar age, smack in the middle of the busiest month for asteroid and comet activity in recent memory. Mere chance? Maybe, but maybe not. The only way to know is through time and patience. By December, when Atlas returns from solar glare, new data will test the connections. Are there hidden links between its trajectory and the asteroid swarm? Are we truly watching independent events? Or will spectroscopic comparisons reveal something more subtle tying them together? If the evidence ultimately shows Atlas is isolated, unconnected to September's frenzy, we're faced with an even bigger revelation. This is just reality. The universe is more connected, more dynamic, and more alive with motion than our Earth-centered view allows us to see. What feels like extraordinary coincidence might be nothing more than our first glimpse of the true rhythm of the galaxy, a reminder that stars and systems are endlessly trading material in an invisible dance across the dark. But before we tackle those sweeping questions, attention must return to Atlas itself, because as autumn reached its climax and the comet drew up to its October meeting with the Sun, something extraordinary was happening. Telescopes began reporting strange signatures, unpredictable behaviors, and bizarre chemistry that no comet in our solar system had ever displayed. What first looked like a straightforward interstellar visitor was starting to rewrite the rules of comet physics itself. The strangest revelations came from the James Webb Space Telescope throughout August and September 2025. Its sensitive infrared instruments saw something no one expected. The glowing coma of 3 Atlas wasn't dominated by water vapor like most comets. Instead, it was nearly overwhelmed by carbon dioxide. The CO-to-water ratio was so extreme, it ranked among the highest ever recorded for any comet, and by current theories, it shouldn't even be possible. To see why, think about how comets normally form. In young star systems, water ice condenses once temperatures fall to around 150 Kelvin, which usually happens in regions a few astronomical units from the parent star, roughly where the giant planets orbit in our own solar system. That's why most local comets are packed with water mixed with other ices. They were born in the cold outskirts, beyond Neptune. Carbon dioxide, however, condenses much farther out, around 10 AU or more, where temperatures dip under 80 Kelvin. In all known comets, CO is always a side ingredient, never the dominant one. That Atlas is almost entirely carbon dioxide suggests it was forged under conditions very different from anything in our Sun's neighborhood. One possibility is that Atlas is the product of a system far larger, or far colder than ours, maybe orbiting a small dim star, or born beyond the reach of multiple giant planets. In such regions, CO-fied ice could form in abundance while water remained scarce. Another idea is that the strange mix is the result of chemical weathering during its incredible voyage between stars. Over billions of years, high-energy cosmic rays may have stripped away water molecules from its surface while leaving carbon dioxide intact, sculpting the object into the bizarre body we see today. Yet that wasn't the only oddity. When the Very Large Telescope in Chile took its turn studying Atlas, it picked up unusually bright nickel lines, but surprisingly weak iron signatures. In our solar system, comets and meteorites generally mirror the Sun in their iron-to-nickel ratio, but here, iron was strangely depleted compared to nickel. That hints at either weird chemistry in its birth environment, or selective loss of iron during its long exile through the galaxy. Maybe nickel proved more stable, or maybe Atlas was born around a star with elemental ratios alien to our own Sun. If so, its origins might lie in the galaxy's thick disk or halo, populations of stars with far different chemical fingerprints than the familiar thin disk where our solar system resides. As Atlas edged toward its close pass around the Sun in October, it wasn't just its chemistry that stood out, its tail grew more elaborate with every passing week. Instruments like those at the Gemini Observatory observed not just one but multiple tails separating into different streams, each distinct in direction, color, and makeup. It was as if different parts of the nucleus were coming alive at different times, releasing distinct volatile reservoirs in a staggered, chaotic process. This was consistent with what physics predicts carbon dioxide sublimates first, flaring at great distances, while water ice only erupts closer in, creating later activity with very different dynamics. Polarization measurements added yet another layer to the mystery. Analysis of scattered sunlight revealed dust grains, unlike those from any typical solar system comet, particles with strange size distributions or optical quirks. That might mean Atlas formed under entirely different initial conditions, or that its dust grains were reshaped and altered during billions of years wandering interstellar space. Even stranger were its light curve flare-ups. Most comets brighten gradually as they close in on the Sun, following neat, predictable curves, but Atlas behaved erratically, undergoing sudden bursts of brightness that seemed disconnected from its distance. These flare-ups suggested pockets of fresh volatile material suddenly exposed beneath the surface. Many comets develop insulating crusts of dust, organic material, and hardened ices that stifle gas release. But when those fragile shells collapse or split apart under thermal stress, the buried ices beneath explode into action, causing temporary surges. Atlas seemed to be doing this in a series of unpredictable pulses. Another explanation points to subsurface fractures. As heat penetrated deep into the nucleus for perhaps the first time in billions of years, buried ices may have cracked, venting gas through new channels. The result cascading internal failures that caused bursts of activity far beyond the smooth curves astronomers expected. Its spin added to the puzzle. Photometric studies measuring subtle brightness shifts struggled to lock down a rotation period. Instead, Atlas appeared either to be spinning extremely slowly or tumbling chaotically. Both possibilities challenged assumptions. Was its structure altered during its ejection from its home system, or had it been battered during its endless interstellar drift, leaving it unstable, asymmetric, and unpredictable? What unsettled astronomers most wasn't the strangeness alone, but the fact that Atlas seemed to toggle between familiar and alien. In some respects it behaved exactly like any comet we know, growing a coma, venting volatiles, forming tails that responded perfectly to solar heating. In others, it deviated wildly, flaunting chemistry and physical behavior that none of our models could comfortably explain. It was at once ordinary and utterly unprecedented. A reminder that even within known physics, the universe loves to tell stories stranger than imagination. The deeper astronomers looked, the stranger 3 Atlas became. Its chemistry, its changing appearance, and its unpredictable behaviors refused to fit neatly into decades of comet research. It wasn't just another icy body passing through the solar system. It was something that forced scientists to rethink how comets form, and perhaps even how planetary systems themselves take shape. Atlas seemed like a messenger from environments utterly different from our own, carrying secrets that could rewrite entire chapters of cosmic history. It was at once familiar and alien, obeying the basic rules of comet physics, while bending them into shapes no one expected. As Atlas crept toward its October swing around the sun, the data pouring in painted a confounding picture. Clearly it was a comet. It vented gas, it flared, it built a distinctive coma and tail. Yet beyond that basic identity, nothing about it lined up with our existing categories. Was this truly something exotic, born under conditions our solar system never experienced? Or was it simply a rare extreme born of chance, an outlier pushed far beyond the normal range of what we've seen before? That question wouldn't be answered until after December, when Atlas would slip out from behind the solar glare and finally offer telescopes their clearest view. But as scientists planned for those crucial observations, a different kind of question started to spread, one less about physics and more about possibility. For some, the timing, the strange chemistry, the bizarre behaviors, and the fact that this object arrived in the middle of one of the busiest months for near-Earth objects in recent memory was just too much. The word natural no longer seemed enough. In the age of endless speculation and viral ideas, some were starting to ask the inevitable: what if 3I Atlas wasn't entirely natural? Could it be technology? It was a line of thought that echoed back to 2017, when the elongated object, Oumuamua, sparked furious debate about possible artificial origins. Just like Atlas, that earlier visitor came from interstellar space and confused astronomers with behavior that didn't align with expectations. Both objects also seemed to arrive with almost suspiciously perfect timing for human observation. But that's where the similarities ended. Oumuamua's odd acceleration, without any visible outgassing, gave rise to speculation that it might be powered. Atlas, by contrast, played the role of comet to perfection. It grew a visible coma and tail, brightened in predictable ways, and moved exactly as a natural comet should, with slight technical deviations explained by jets of gas escaping as it heated near the sun. Most importantly, its motion showed no course corrections, no deliberate maneuvers, no hint of control, no unexplained signals came from it, no radio transmissions, no structures. Through the lens of the scientific method, extraordinary claims demand extraordinary proof, and everything observed about Atlas, even its most puzzling qualities, fit within natural explanations. The overwhelming surge of carbon dioxide in its coma likely pointed to a strange birthplace, perhaps the frozen edge of another system where water ice never condensed in large amounts. The lack of iron compared to nickel could have been shaped by an alien stellar environment, or by billions of years of radiation damage in interstellar space. Its chaotic brightening events and complex tail behavior while extreme had precedence in other comets. Hale-Bopp sported multiple tails of different compositions. Comet Holmes erupted spectacularly in 2007, brightening a millionfold almost overnight. The universe already provided plenty of natural pathways to explain Atlas without invoking machines or civilizations. But despite this, public fascination zeroed in on artificial origin theories. The reason was psychological as much as scientific. When we encounter a phenomenon that defies our expectations, especially one from beyond our solar system, our brains instinctively lean toward ideas of purpose and intelligence. It's the same mental wiring that helped humanity survive by spotting predators and recognizing intention in the behavior of others. Faced with the alien and unfamiliar, pattern-hungry minds start whispering, maybe someone made this. Compounding this tendency was the media ecosystem surrounding discoveries like Atlas. Stories framed as mysterious object baffles scientists spread faster and captured far more attention than cautious headlines about strange but natural comets. Social platforms amplified the effect, fueling speculation before data could even be fully analyzed. This cycle was all too familiar. Pulsars discovered in the 1960s were briefly thought to be alien signals before proven to be distant neutron stars. Fast radio bursts followed the same trajectory: mystery, speculation, then natural explanation. The pattern repeated itself, and Atlas was simply the latest chapter. The truth was far more intriguing than conspiracy. Every piece of evidence lined up with the idea that Atlas was a natural fragment of another planetary system. It wasn't artificial. It was authentic. A real sample from outside the sun's domain. Theoretical models have always predicted that stars shed tremendous amounts of debris during their formation. Billions of chunks like Atlas should be wandering the galaxy, ejected during violent birth processes and drifting forever through interstellar night. Every now and then, one cuts across our solar system. Atlas was one of those. Its alien chemistry wasn't a trick or a signal. It was proof we were finally beginning to see other systems' fingerprints in the material they cast off into the dark. So while the evidence didn't point to extraterrestrial technology, it pointed towards something just as profound. Atlas was an invitation to study how other worlds formed, shaped under different stars with unfamiliar ratios of elements, different planetary layouts, different histories of heat, light, and collision. Its strangeness wasn't a product of design. It was a product of diversity. It reminded us that our solar system is only one story among countless others spinning through the galaxy. And that left only one greater mystery to solve. If Atlas was natural, then where had it spent its billions of years before arriving here? What path had it traced across the Milky Way? What family of stars had cast it out into the void? And what cosmic lottery had delivered it to Earth's skies at just the right time for us to study? Already, astronomers were trying to run the numbers backward, to trace its path through the tangled flows of stellar motion across galactic timescales. The answers were incomplete, but tantalizing. Atlas, it seemed, was not only carrying chemistry from another world, it was carrying a story billions of years in the making, one that may soon reveal just how connected we really are to the wider galaxy. Reconstructing the backstory of 3I Atlas is like piecing together the life of a traveler older than Earth itself. Inside its frozen chemistry and etched into its hyperbolic path lies a record of events that began billions of years ago, when the Milky Way was young, and stars were forming under conditions very different from those we see today. Following its biography means retracing a journey that spans galactic eras, a timeline where entire civilizations might have risen and fallen while this object simply drifted. The first hints about its birthplace came not from its chemistry, but its motion. Careful attempts to trace Atlas's path backward through time suggested it may have originated in the galactic thick disk, a population of stars that formed 7 to 12 billion years ago. If true, that would make Atlas older than the Sun itself. It would have left its home long before our solar system existed, carrying with it chemical fingerprints from a galaxy still in its turbulent youth, when the mix of heavy elements was dramatically different from what we see now. The strange depletion of iron and the overwhelming dominance of carbon dioxide fit this theory, consistent with the chemistry of stars born in that ancient population. But how does a body like this get ejected into the void? The story begins during the chaotic early years of planetary birth, when giant planets shift positions, migrating inward or outward through the haze of a newborn planetary system. They often fling smaller objects into deep space. Simulations suggest this isn't rare, it's inevitable. For every single kilogram of matter that remains bound as planets or comets, perhaps 10 kilograms are thrown out forever. The galaxy then should be filled with trillions of such wanderers, icy relics abandoned by their parent stars, slowly drifting between suns. Atlas appears to be one of them. Once cast out, its journey would have carried it through a vacuum so empty, it makes even the best human-built chambers look crowded. With only 1 atom per cubic centimeter on average, interstellar space became its graveyard and preservative, a cosmic freezer keeping its ices intact for nearly unfathomable spans of time. But empty doesn't mean uneventful. Models of galactic motion suggest Atlas passed close to several other star systems during its voyage. Over the last 10 million years alone, it seems to have drifted within a few light years of multiple stars. One particularly close brush came about 4 million years ago, when it passed near a red dwarf in Cassiopeia. That flyby may have changed its course just enough to send it on its current path toward us, erasing much of the direct signature of its original home. Meanwhile, the universe was still etching changes onto its surface. Intense galactic radiation, supernova blasts from afar, and collisions with dust grains slowly rewrote the chemistry of its outer layers. High-energy particles would have broken apart molecules and sculpted entirely new isotopic ratios, strange fingerprints absent in solar system comets. Yet, paradoxically, the extreme cold of interstellar space preserved Atlas. Its core remained practically untouched, sealed in ice at temperatures mere degrees above absolute zero. Over billions of years, microcracks may have healed through cycles of sublimation and refreezing, giving it the resilience to survive its cosmic exile. That survival makes its timing all the more staggering. For Atlas to reach us now, in this exact moment when humanity finally possesses the telescopes to study it properly, feels improbably perfect. A few centuries earlier, it would have passed as just another faint fuzz in the sky. A few centuries later, and although we might have detected it, we may not have had the tools to understand what made it unique. Yet now, as James Webb and ground-based behemoths scan the heavens with unmatched precision, the visitor arrives. After billions of years in darkness, it reached Earth's skies during the one blink of history when we are ready to see it. Its biography also mirrors the biography of the galaxy itself. Every atom inside Atlas, its carbon, oxygen, silicon, its scattered metals, was forged in the hearts of ancient stars, then blasted outward by supernovae before condensing into a new planetary system. In studying Atlas, we're not just examining a piece of rock and ice, we're touching the accumulated history of entire generations of stars. It isn't just debris, it's testimony, a fossil of other worlds. The thick disk origin theory, if borne out, would mean that Atlas is not just old, it's primordial, a relic from a chapter of the Milky Way when stars formed at a furious pace, and the chemistry of interstellar space was far less enriched. Studying it could unlock missing pieces in our models of galactic chemical evolution, showing us how diversity in star systems drives diversity in planetary systems. It carries clues about how volatile elements behave under conditions that Earth's family of worlds never experienced. Yet, even with all this analysis, vital mysteries remain. We may never know precisely which star birthed Atlas, or what planetary system expelled it. The galaxy has wiped away those breadcrumbs with time. Galactic chaos constantly scrambles orbits. Stars orbit the Milky Way's center like dancers weaving in and out of one another, erasing past alignments. What's left are statistics, probabilities, faint echoes pointing to its ancient home. Interstellar archaeology is an act of inference. Unlike fossils in Earth's rocks, these cosmic fossils come detached, stripped of context. Their past must be deduced from chemistry, dynamics, and modeling. Atlas forces us to reconstruct its epic life from clues scattered across the sky. By late October 2025, Atlas reached the brink of its closest approach to the Sun. That was the moment of maximum activity, when its long-buried ices would roar into space in a display that might reveal its inner secrets. But just as it became most alive, the Sun's glare concealed it, hiding the comet at the very moment astronomers most wanted to watch. Would it survive this fiery encounter? Would it fracture into fragments, carved apart by tidal stresses and solar heat, like so many comets before it? Or would it endure, intact, carrying its strangeness forward into December skies for us to probe again? For now, those answers were still hidden. What was certain is that Atlas's story, interwoven with September's surge of comets and near-Earth asteroids, was reshaping how humanity thought about the neighborhood we inhabit. Were these coincidences of timing, an unlikely pile-up of chance encounters, or were they subtle patterns hinting that larger dynamics were at play in our solar system and beyond? To some, September felt like more than a statistical fluke. It felt like a curtain lifting, the beginning of a drama on scales beyond human comprehension. Imagination quickly filled the void. If Atlas could survive from the dawn of the galaxy to our telescopes, what bigger cosmic chain reactions might it have set in motion, simply by passing through? Was this one object, however small, capable of stirring up our solar system in ways we had yet to realize? These questions became the launching point for even wilder speculation, cosmic domino effects that hinted at possibilities too vast and too spectacular to dismiss outright. The math leaves no room for magical thinking, even at the upper bound of its estimated mass. Several trillion kilograms, three-eyed Atlas is a featherweight in the arena of solar system dynamics. At distances of millions of kilometers, its gravitational pull is laughably insignificant when compared to the colossal dominance of the Sun, or even the tug of planets. Newton's inverse square law is merciless here. The further you get, the weaker the force, dropping to the point of irrelevance. In fact, during the same weeks that Atlas and the asteroid FA-22 both occupied the inner solar system, their mutual attraction was about the same as two parked cars pulling on each other from different cities. The numbers crush the romance of gravitational shepherding in one stroke. And yet, despite the physics, such theories persist. Why? Because humans are hardwired to connect dots. When unusual events occur together, we instinctively look for links, even where none exist. That instinct was a survival tool in ancient times, helping our ancestors identify predators and cause and effect relationships. But when projected onto cosmic scales, it misleads us, suggesting connections that the universe simply doesn't make. Some speculations stretched even further, beyond gravity, into the realm of solar activity. The idea was whispered: could an interstellar intruder somehow stir the Sun itself, triggering solar flares or coronal mass ejections capable of frying satellites and disrupting power grids on Earth? The concern is understandable. Modern life is vulnerable to solar storms. But here again, the numbers are merciless. The Sun produces 380 sextillion watts of power every second, far more energy than all of human civilization has ever consumed, summed across history. Whatever influence Atlas exerts from more than 100 million kilometers away is entirely washed out by the Sun's own colossal electromagnetic and gravitational engines. Solar flares, sunspots and cycles are born of the Sun's magnetic dynamo, not comets wandering by. Any overlap in timing between comet appearances and solar outbursts is coincidence, statistical noise mistaken for cause. Then came the meteor shower idea, offered with the same excitement. If Earth passed through debris trailing Atlas, might we see dazzling interstellar meteor storms lighting our skies? Tempting in theory, but the physics make it a non-starter. Debris leaving Atlas would carry the same hyperbolic escape velocity as the comet itself, meaning the particles will flee the solar system rather than linger in a stream that Earth could cross annually, as happens with local comets like Swift-Tuttle or Tempel-Tuttle. And even if particles could somehow intersect with Earth, they'd be moving at suicidal speeds. 70 kilometers per second or more. Impacts at that speed wouldn't create graceful drifting streaks across the sky. They'd flash violent and fast, disappearing before a human eye could even track them. Another favorite conspiracy thread narrative was fragmentation. The idea that FA-22 and other near-Earth asteroids spotted in September weren't independent bodies, but pieces of Atlas itself, broken off in some previous pass. But orbital mechanics forbids this. True siblings of Atlas would keep its hyperbolic flight path, and their chemistry would scream interstellar origin. Instead, the September asteroids exhibited plain, conventional orbits and typical carbon-rich or silicate compositions. They belong to our solar system, not to Atlas's shadowy past. Other theories dipped into darker waters, that governments or agencies were hiding something. Was Atlas doing something extraordinary that agencies weren't telling us about? In an era of mistrust, it's an easy speculation, but the structure of astronomy itself undermines the idea. Data flows openly. Observatories post schedules, publish orbital elements in public databases, and share follow-up results with international networks in days. Amateur astronomers in backyards worldwide join the hunt, cross-confirming discoveries for no reason other than passion. To stage a cover-up would require silencing thousands of professionals and enthusiasts across dozens of countries, something utterly impossible in the hyper-competitive environment of science. What the data shows is clear. Everything about Atlas fits natural behavior, even if it pushes that definition to extremes. But dismissing conspiracy doesn't mean dismissing wonder, because one what-if remains very real and very compelling. What if Atlas isn't rare at all? For decades, interstellar visitors seemed like a once-in-a-lifetime phenomenon. Oumuamua in 2017, Borisov in 2019, and now Atlas. But maybe our perception has been skewed by our limited vision. With the Rubin Observatory scanning the skies every few nights, with infrared space telescopes like NEO-Surveyor set to launch, and with global networks of astronomers coordinating in real time, we may soon discover that the galaxy is littered with these objects. Simulations suggest every planetary system ejects mountains of debris into interstellar space during its formation, enough to seed the galaxy with trillions of wandering fragments. It's possible that, instead of one interstellar comet every decade, we might be on the verge of detecting 10 or even 20 per year. If that's true, the late 2020s could herald a revolution. Interstellar archaeology, once restricted to rare anomalies, might become a systematic science. We could begin cataloging the chemistry of comets from other stars as casually as we log near-Earth asteroids today, each one a message in a bottle from another system, carrying the fingerprints of alien worlds and stars long since vanished. This would transform our understanding of cosmic belonging as profoundly as Copernicus once did. No longer would we see Earth and our solar system as isolated products of a single star's story. Instead, we'd recognize ourselves as part of a galaxy-spanning exchange where material flows between systems constantly, trading fragments of planets and stars over cosmic scales. The September surge, seen in this light, may not have been a statistical anomaly at all. It may have been our first glimpse of the truth. Our local neighborhood is not quiet, not rarefied, but alive with the debris of a galaxy that never stops moving material from place to place. And as thrilling as those implications are, they were overshadowed by one urgent reality. Atlas was racing toward its perihelion, the point of closest approach to the Sun, where the real test would begin. Would it survive its fiery encounter intact, revealing more of its alien chemistry, or would it shatter, leaving behind nothing but a cryptic cloud of fragments? For astronomers, these coming weeks meant more than satisfying curiosity. They promised the decisive data needed to understand whether Atlas could hold its secrets through the furnace of its brief solar encounter, or whether it would dissolve, taking those secrets back into the dark, leaving us only questions and fleeting memories. If 3I Atlas disintegrated while rounding the Sun, humanity's chance to study pristine interstellar material could vanish for generations. Another such visitor with favorable geometry might not come along for centuries, but survival would mean something extraordinary. Its reappearance in December could unlock the most detailed glimpse of alien material in history, a direct sample from another star system preserved in ice and dust. By late 2025, the cosmic drama was nearing its most critical moment. October 30th marked the date of perihelion, the closest approach between this billion-year-old wanderer and our Sun. After drifting silently through interstellar darkness longer than Earth itself has existed, Atlas was about to face its greatest trial. Yet at the very time it would reveal the most, when solar radiation boiled its ancient chemistry into view, it vanished from Earth's sight, swallowed by the Sun's glare. This was the cruel irony. The best opportunities for discovery arrived, just as the object became invisible. At perihelion, Atlas was less than half an astronomical unit from the Sun, closer than Mercury. From Earth it lay buried within 10 degrees of the Sun's searing light, an impossible place for telescopes to watch. During this hidden phase, it could either endure the fire and emerge intact, or collapse into shards, scattering the very secrets astronomers hoped to study. Its survival wasn't a trivial question. It was a test of whether interstellar objects could preserve their original chemistry even under the most brutal solar heating. Fragmentation, while dramatic, would rob scientists of the pristine data locked inside, turning a cosmic time capsule into drifting ruins. History offered little certainty. Many solar system comets do shatter on their first brush with the Sun after eons in cold storage, but Atlas was no fresh rookie. It had survived long beyond its star of origin, endured cosmic rays, supernova blasts, and billions of years in the void. Some believed this hardiness was its greatest defense. Others cautioned that even a hardened traveler could split apart when faced with the Sun's relentless power. The irony deepened. After traveling across unimaginable expanses, Atlas would hide behind the one celestial body that forced it to reveal its deepest chemistry. Like a star disappearing behind the curtain at the climax of a concert, the comet would perform its defining act unseen. Yet patience is part of the astronomer's creed. Earth's motion around the Sun would gradually shift the viewing angle. By early December, Atlas would rise again from the glare, creeping into the pre-dawn skies in perfect alignment for global observatories to capture every detail. At that point, it would approach within 1.8 astronomical units, 270 million kilometers. For earthly scales, vast, but for telescopes, ideal, close enough to gather ample light and spectra, far enough to avoid interference from Earth's background glow. This window could become the greatest opportunity humanity has ever had to study intact interstellar matter, and unlike Oumuamua, which slipped away swiftly, or Borisov, which grew faint soon after discovery, Atlas's path and velocity meant it would linger well into 2026, giving scientists months of observing time across multiple wavelengths. Meanwhile, the other cosmic players of 2025 weren't idle. Comet SERS 2025 R2, discovered by the SWAN instrument, continued inching toward its own perihelion in early November. Like many fresh Oort cloud arrivals, its survival was uncertain. If it held together, it could blossom into a beautiful spectacle visible without telescopes, a glowing greenish coma, tails unraveling across the dark skies of the northern hemisphere. If not, it might shatter like so many fragile snowballs before it. Even under small binoculars, comet watchers were already reporting delicate green glows and fine tails, a classic sign of volatile ices vaporizing under sunlight. Farther away, asteroid 99942 Apophis continued its slow approach toward its infamous 2029 flyby. The closest a rock of its size will come in recorded history. Though still years away, its study was already underway. Ground-based telescopes began detailed campaigns to analyze its surface and rotation before the close pass alters both, and NASA's repurposed OSIRIS-APEX spacecraft steadily adjusted course for its rendezvous after Apophis's Earth encounter, prepared to map how planetary gravity reshaped the asteroid forever. Meanwhile, humanity's surveillance network leapt forward. The Vera C. Rubin Observatory, still in its commissioning phase, was already producing breathtaking results. Its first scans revealed thousands of new near-Earth asteroids within hours, hinting at the revolutionary observational cadence it will soon deliver. Once fully operational, Rubin will rescan the sky every few nights, offering a near real-time feed of cosmic traffic. What once looked like clustering may soon be revealed as the everyday reality of a crowded neighborhood, events not unusual, just previously invisible. And beyond Earth's atmosphere, a new line of defense was preparing to rise. NASA's NEO-Surveyor, scheduled for its 2027 launch, will finally close the deadliest blind spot, objects approaching from the sun's direction. From its outpost trailing Earth in orbit, it will peer into the very corridor that once hid the Chelyabinsk impactor. With advanced infrared eyes, it could give us the time we need to turn planetary defense from a hope into a guarantee. For ordinary enthusiasts, late 2025 also offered unmatched opportunities to contribute. Amateur telescopes were capturing Comet SWAN, recording its tail as it lengthened and shifted. Soon, astrophotographers in the southern hemisphere would get first chances at Atlas once it returned in December twilight, followed by northern skywatchers as it climbed higher. Even without giant observatories, coordinated small-scale observations were becoming invaluable contributions, helping distribute coverage and track sudden changes. As Atlas moved toward its date with the Sun, the mobilization of the global scientific community had become an unprecedented rehearsal for both discovery and defense. The same international protocols guiding the study of this interstellar comet would one day shape how we respond to genuine impact threats. The September surge of asteroids and the looming presence of Atlas had forced nations and observatories to coordinate as never before, building a framework that could prove essential when the stakes extend beyond knowledge to survival. For scientists, the December window wasn't just another observation. It could be the most important opportunity of their lifetimes. Beyond the thrill of discovery, the data promised insight into galactic history, planetary birth, and the ancient chemistry that shapes worlds. But everything hinged on survival. Would Atlas endure its fiery test long enough for us to peel back its mysteries, or would it break apart, snuffing out answers just as we were ready to hear them? By the late 2020s, a powerful combination of tools, the wide sweeps of the Vera Rubin Observatory, paired with heat-sensitive eyes of space-based telescopes like NEO-Surveyor, had turned skywatching into something close to total awareness. With these systems working together, humanity could spot potential threats not just months or years, but decades and even centuries ahead of time. That kind of lead time changed the entire game. Suddenly, asteroid deflection was no longer the stuff of desperate last-second missions and Hollywood thrillers. It became manageable, repeatable, more like monitoring hurricanes or tracking earthquakes than fighting impossible odds. a small, controlled nudge years in advance, using perfected kinetic impactors inspired by NASA's DART test, could tweak a rock's orbit just enough to move it safely out of harm's way. Planetary defense shifted from panic to procedure, space traffic control on a cosmic scale. In this hopeful scenario, every piece of the puzzle fell into place. Comet Swan glided smoothly through its fiery pass by the sun, and blossomed into a dazzling green spectacle that lit up winter skies, inspiring ordinary skywatchers, and rekindling global fascination with the cosmos. 3I Atlas survived its own perilous encounter, and when it resurfaced in December, telescopes captured the most intimate direct measurements of interstellar material ever achieved. That single object gave birth to an entirely new scientific field, interstellar archaeology. Before long, upgraded surveys were finding not one or two, but dozens of visitors from other star systems, each carrying strange and unique chemical fingerprints. By the early 2030s, these findings had built up a galactic library of planetary ingredients, direct evidence of how different stars and different environments shaped their worlds. The fallout was not only scientific but technological. New techniques in spectroscopy, astrometry, and orbital prediction blossomed, sharpened both for discovery and for defense. Humanity had for the first time begun to read the biographies of other planetary systems in detail. At the same time, public trust in science soared. The protocols born from observing Atlas matured into full-fledged frameworks for planetary defense, agreed upon and rehearsed through international drills and exercises. People around the world were engaged like never before, tuned into live streams of discoveries, following orbital updates, watching cosmic events unfold in real time. For many, it was proof that global cooperation and research could truly protect humanity from one of the last uncontrollable forces of nature. But the future doesn't only offer smooth sailing. A more sobering path imagines improved detection will indeed expand our hazards list, but eventually one of those city-killer asteroids, 100 to 300 meters across, will appear with barely enough warning to act. Unlike the giants over 1 kilometer that we have largely catalogued, this deadly middle class of asteroids remains worryingly incomplete. Statistically, one will eventually line up against Earth, and when it does, there may not be years to prepare, only weeks or months. Such a scenario would force humanity into high-pressure, high-stakes decision-making, likely turning to stronger interventions, nuclear standoff detonations, experimental propulsion beams, or crash course missions. Success in such a test would prove the worth of planetary defense beyond doubt, and push governments into boosting funding and technology. But failure could cost millions of lives, and sow doubt in humanity's ability to protect itself. Even partial successes could be deeply complicated. A nudge that redirects an asteroid away from a city might still scatter fragments into multiple smaller impacts. City-sized damage could be traded for region-wide scars. In such moments, perception could shift. Would people view planetary defense as heroic intervention, or reckless tampering with forces beyond our control? Another dangerous wildcard lies at sea. Most of Earth is covered in water, which means statistically, most incoming impactors will aim there. But tsunamis born from ocean strikes remain one of the hardest things to model with confidence. A 200-meter asteroid, plunging into the Atlantic, could send waves 10 meters high surging toward coastlines on both sides. Even if warning systems bought hours for evacuations, the social and economic costs would be immense. Vast swaths of coastline, millions of livelihoods would be transformed by displacement, flooding, and destruction. And then there are the nightmare scenarios. Rare, yes, but not impossible. A long-period comet from the Oort cloud could appear with only months to spare, moving faster and carrying more energy than anything we've yet encountered. Such an object, 10 kilometers across or more, would unleash devastation on a scale humans cannot currently deflect. Kinetic strikes wouldn't be enough. Nuclear blasts might help, but the timelines for developing and deploying the needed systems could easily exceed available warning time. These world-ending rocks remain the ultimate astronomical wildcard, statistically rare, but catastrophic beyond comprehension. Planetary defense can reduce risk, but not erase it. Like earthquakes or volcanoes, the goal is resilience, not invincibility. Beyond the technology, the human factor complicates everything. Public trust, media narratives, and government coordination matter as much as physics. Clear, accurate messaging from scientists and agencies can prevent chaos when a threat is identified, while reckless headlines and online conspiracies can undermine even the best technical solutions. The September surge of 2025 showed how fast misinformation can spiral around cosmic events. A real impact warning would multiply that confusion 100-fold. How humanity speaks about these threats could prove just as critical as how it responds to them. There are also competing interests to consider. The commercial space sector is racing to mine asteroids, driven by profits. In principle, the technologies developed for extraction, surveying, rendezvous material testing could double as planetary defense tools. But money and safety don't always align. The discovery of a resource-rich near-Earth asteroid with hazardous potential could spark disputes between deflection priorities and mining ambitions, which takes precedence: global security or corporate claims. Resolving these conflicts will demand a new generation of international regulation, ensuring that space's commercial future doesn't compromise humanity's survival. And politics, of course, lurks behind every scenario. When a real crisis comes, will nations stand together to stop a rock or splinter into competitive responses, each trying to save itself or claim responsibility for heroism? The cooperative frameworks in place today might hold under pressure or fracture when tensions rise. Humanity's ability to think and act as one species against a common external threat remains one of the greatest uncertainties. The future could lean toward triumph or tragedy, resiliency or fragility. Advances in artificial intelligence, propulsion, and even nuclear fusion might make asteroid deflection routine and reliable. But cuts to funding, stagnation, or fractured politics could leave us dangerously exposed. In the end, the story of planetary defense is not just about rocks in the sky, it's about us, how we organize, how we prepare, and how we face the cosmos together. Planetary defense and interstellar science don't exist in a vacuum. They compete for the same limited political attention and financial resources already strained by climate change, inequality, environmental collapse, and global conflict. Asteroid impacts may seem distant or abstract compared to collapsing economies or rising seas, and that makes prioritization difficult. Yet objects like 3 Atlas offer something that no other issue can: a perspective big enough to unite. They remind us that Earth isn't just a stage for human rivalries, it's part of an active galactic system where ancient debris passes by, where threats and opportunities drift into view, and where survival depends on cooperation beyond borders. That perspective could become one of humanity's most valuable tools, inspiring collaboration that transcends the divisions holding us back. The futures we shape in the coming decades will depend as much on our social imagination as on our telescopes. The September surge and the passage of 3 Atlas were not simply scientific events. They were a mirror, showing us both how far we've come and how far we still must go. But before we can speculate on centuries-long outcomes, one immediate truth remains: we have to see what Atlas reveals when it re-emerges in December. Its chemistry and physical state could offer humanity its first real taste of material birthed in another star system, and with it, the clearest sense yet of what it means to live in a galaxy alive with exchange. As winter settles across the northern hemisphere, and scientists prepare for Atlas's reappearance from behind the sun, we stand at a genuine turning point. The events of September did more than expand our data sets. They changed how we think about existence. For millennia, the night sky bred an illusion of permanence. Stars wheeled in unchanging patterns, planets crept predictably, and only the occasional comet reminded us of motion. To early humans, Earth felt isolated, its fate bound only to local stars and stones. But this year shattered that illusion. Our solar system is no quiet suburb. It's a crowded intersection where ancient messengers from distant suns rush through, bearing secrets carved at the dawn of time. 3 Atlas alone is a direct thread to an era long before our sun formed. Its chemistry is a fossil record of alien environments, encoding conditions billions of years old that shaped stars and worlds in corners of the galaxy we may never travel to. This changes more than science. It changes perspective. Just as Copernicus revealed Earth wasn't the center of creation, Atlas shows us we're not isolated. We are participants in processes spanning the entire galaxy, processes that exchange materials, stories, and perhaps even life between worlds. Every spectral reading from Atlas is more than a measurement. It's a sample of galactic history, a record of how stars forged elements and how matter condensed into planets under conditions alien from our own. With tools like the Vera Rubin Observatory and NEO Surveyor, we've proven we can find, track, and deeply study cosmic visitors, not as bystanders, but as active archaeologists of the galaxy itself. Humanity has crossed a threshold, from looking up in wonder to reaching out with purpose. The implications stretch far beyond astronomy. The same infrastructure built to detect asteroids and probe comets, global detection networks, fast responses, international coordination, are exactly the mechanisms needed to face other shared crises. The playbook for tracking a rogue asteroid could one day guide how we track carbon in the atmosphere, viruses on the move, or the depletion of oceans. Science, technology, cooperation, it's all the same toolkit for survival. Atlas and the September surge prove these lessons in ways no local crisis can. They show us that looking outward teaches us how to endure here at home. The deeper truth is humbling. Every atom inside us comes from stars that died before the sun was born. The water we drink may have been delivered by comets not unlike Atlas. The air we breathe has cycled through interstellar clouds for billions of years. Awareness of this galactic context turns environmental stewardship and global unity into something more than ideals. They become practical necessities. If we fail to preserve the rare, fragile conditions that allow life here on Earth, we may fail the very cosmic chemistry that created us in the first place. Yet, the surge also highlights how much we still don't know. Astronomers used to assume interstellar visitors were rare, maybe one detectable object every few years. But what if Atlas isn't an exception? What if it represents normal levels of activity, and with better tools, we'll see dozens or even hundreds slipping past us every year? That shift would completely alter our picture of galactic material exchange, and by extension, the odds that organic chemistry and perhaps biology are scattered far and wide across space. Every comet entering our system is a laboratory in motion, carrying pieces of chemical puzzles we can't recreate in earthly labs. Each one is a chance to see how other systems build the raw ingredients of worlds. But seizing these chances requires constant vigilance, upgrades, funding, and political will. The capacities that spotted FA-22, tracked Swan, and flagged Atlas weren't accidents. They came from decades of science, international collaboration, and long-term funding. If we allow attention to drift in the quiet intervals between spectacular events, the opportunities will slip past us unseen. Atlas is a reminder that our neighborhood is more active than we imagined. We've barely begun to uncover patterns operating at galactic scales since long before Earth's first sunrise. The choice now is simple but profound. We can embrace this new role as citizens of a galaxy in motion, investing in the observation networks and international partnerships that protect us and expand our knowledge. Or we can squander the perspective we've just gained, retreat into short-term rivalries, and pretend the cosmos isn't knocking on our door. The September surge and Atlas most of all call us toward the first path: curiosity, cooperation, and commitment. The cosmos has handed us an extraordinary gift, a fragment of another star system, arriving exactly when we are finally ready to study it. Whether we learn from that gift, whether we act with the wisdom to preserve our world and expand our understanding, will determine whether humanity remains a local species bound to one star or steps fully into its role as an aware participant in a galactic civilization of matter, chemistry, and time. Atlas's re-emergence won't just reveal the secrets of another system, it will reveal something about us, our priorities, our cooperation, and our vision of the future. The September surge was only the opening scene. The story ahead stretches across billions of years and billions of stars, and for the first time, we have a chance to read it.